Hello children. In this session, I am going to continue with the topics of electric potential. On the last day, we derived expression for electric potential due to a point charge. We derived expression for electric potential due to a system of point charges. And also we derived expression for potential due to a dipole. Today I am going to continue with the topics of electric potential. The very first, I am going to establish the relationship between the electric field and potential. So mathematically we are going to show electric field will be the negative gradient of potential. What I am going to prove here is electric field will be equal to the negative of potential gradient. That is, I am going to write it as dV by dr. Before getting into the derivation, I think you know what is gradient of a physical quantity. In 11th also the term gradient you came across viscosity, you came across thermodynamics. So there you came across velocity gradient, temperature gradient. So I am going to make a very quick recap of what is gradient. So what is gradient of a physical quantity? Obviously it is the variation of that physical quantity with respect to distance. Say if it is velocity gradient, I am going to write it as dV by dx. Variation of that physical quantity with respect to distance represents gradient of that physical quantity. Similarly, if I am going to say for temperature, I can write it as dt by dx. So similarly, by extending the same logic, so what is potential gradient can be written as dV by dr. Instead of x, we are using dr. So we are going to prove E is equal to minus dV by dr. So I am going to start from the same concept that we did for deriving electric field due to a point charge. The same logic we are going to follow. So I am going to assume origin in which a positive charge plus q is placed. I am going to consider 2 points. One is P, another is Q. What about the distance of P is R. What about the distance of Q is R minus dr. I am going to assume it is R minus dr. Next, I am going to keep a test charge at P. My aim is to move the test charge from P to Q. So you know the work done can be expressed in terms of potential difference also. So I am writing, before writing, let the potential at P be V. What will be the potential at Q? I am writing it as V plus dV. So once again I am going to explain the diagram. I am going to consider a charge plus Q at the origin. We consider 2 points P and Q. They are at distances R and R minus dr from the origin. At P the potential is V. At Q the potential is V plus dV. So what is the work done in moving a test charge Q naught from P to Q? I am going to establish in terms of potential difference. You know what is the potential difference? I can write it as the final is V plus dV minus the initial is V. So this is the difference in potential is equal to, obviously it is a small displacement. So I am writing dW is the small work done on the test charge Q naught. So I am writing this equation based on the formula VB minus VA is W by Q naught. From this I am writing this equation. Yes. Now I am going to mark it as, after simplifying, VV cancels. So I can assume dV is equal to dW by Q naught. Mark it as equation number 1. Once again, this is the potential difference in moving a test charge from P to Q. So it is V plus dV is the final potential. V is the initial potential. So V plus dV minus V is equal to dW by Q naught. So VV cancels. So I am getting dV is equal to dW by Q naught. Mark it as equation number 1. On the last day, while deriving an expression for electric potential due to a point charge, I asked you to make a recall of a formula. We derived dW is minus Q naught E dr. I think you can recall this. We derived this while deriving the expression for electric potential due to a point charge, but once again I am going to derive. You know what is the small work done? dW is F vector dot dl vector F vector was minus Q naught E vector dot dl vector. Next, you remember the dot, Q naught E dl cos 180. Ultimately cos 180 is minus 1, so it becomes Q naught E dl. Then you did approximation, dl is minus dr, put it back, so you got dw is equal to minus Q naught E dr, and I am using this. Yes. Once again, what is the small work done? dw is minus Q naught E dr. Mark it as equation number 2. Put 2 in 1. Put 2 in 1. What will happen, you say? So dv is equal to, in place of dw, I can write minus Q naught E dr by Q naught. You know Q naught cancels. So I am getting E can be written as minus dv by dr. Can be written as minus dv by dr. Once again, it is the relationship that shows that electric field is the negative gradient of potential at any point. Once again, I am going to repeat the entire derivation. We are supposed to establish electric field as a gradient of potential, and finally we are going to get electric field will be the negative of potential gradient at that point. So how to start? I am going to consider a charge plus q placed at the origin. I consider 2 points P and Q. They are at distances r and r minus dr from the origin. Let V and V plus dV be the electrostatic potential. Now, what will be the work done in moving a test charge Q naught from P to Q can be established in terms of potential difference. So what I am writing the potential difference, what is the final potential is V plus dV, the initial potential is V, so the difference in potential is V plus dV minus V is equal to dW by Q naught. So I am getting V cancels off, so dV is dW by Q naught, mark it as equation number 1. Already we established while deriving the expression for electric field due to a point charge, that is the small work done can also be written as minus Q naught E dr. By putting this dW in equation 1, we are getting a very simple relation that shows the electric field is the negative gradient of potential at that point. Now, I am going to discuss some of the important conclusions of this expression. So, what is the first thing the expression says? The electric field is the negative, electric field at a point is the negative gradient of potential at that point. So, what is the first information I am getting? Electric field at any point is the negative gradient of potential at that point. Number 2, what I can say, what is the significance of negative sign? The negative sign shows that the electric field, the direction of electric field is in the direction of decrease of potential. Once again, it's a very important concept. Once again, what is the significance of this negative symbol? The negative sign clearly says that the direction of electric field will be in the direction of decrease of potential. Number 3, potential gradient. Now we involved a new term, that is potential gradient. So potential gradient is a vector quantity, whereas potential is a scalar quantity. Potential gradient is a vector quantity and its direction is opposite to E vector. And ultimately the last, what is the unit of potential gradient will be volt per meter. That is, it is measured in volt per meter. So with this I am going to conclude the first topic, that is electric field as the gradient of potential. Next, I am going to derive an expression for electrostatic potential energy. My aim is to derive electrostatic potential energy for a system of point charges. Once again, we are going to derive expression for electrostatic potential energy for a system of point charges. So, you know what is electrostatic potential energy. Electrostatic potential energy, how to define electrostatic potential energy? Let us suppose that I want to define potential energy of a 2-point charge system. Say Q1 and Q2. So how to define electrostatic potential energy? You remove Q1 and Q2 from their location. Let us suppose that Q1 and Q2 are not in their location. They are at infinite separation. Now you bring the charges from infinity to the respective location. That work done gives electrostatic potential energy of the system of charges. So once again, electrostatic potential energy of a system of point charge is defined as the amount of work done in bringing the charges from infinity to their respective location. Now we are going to derive an expression for electrostatic potential energy for a 2-point charge system. Then we are going to extend it for n cases. So how to start? So let us suppose that I am going to assume a coordinate frame. Say it is x, y, z. I am going to assume two locations, two positions, say A and B. Let a charge q1 is placed at A, q2 is placed at B. What about the position vector for q1 is r1 vector? What about the position vector for q2 is r2 vector? So once again, I considered a coordinate frame in which I am going to assume two charges, point charges q1 placed at A with position vector r1 vector, q2 placed at B with position vector r2 vector. Now, in order to define the electrostatic potential energy, as per the definition we said, initially the two charges are not in their respective location. They may be displaced at infinity. I am going to assume they are not in their respective location. They are at infinite separation apart. So let us suppose that q1 and q2 are not in their positions. Now say they are at infinite separation apart. So I am assuming like this, q1 and q2. Now you bring q1 from infinity to A. You bring q1 from infinity to A. This means you should say, is there any work done in bringing q1 from infinity to A? The answer is no, because in the system there were no other charges that can cause an electrostatic force of opposition for the charge q1. So once again, q1, while bringing q1 from infinity to point A, no work is done. The reason is there were no other charges present in the system that causes an electrostatic force, the opposition of electrostatic force on q1. Now similarly, bring q2 from infinity to B. So while bringing q2, I think you can have a very clear guess, work has to be done because q1 had already occupied its position. So it creates a potential at B, and that will surely cause an opposition, and that leads to work done. We are going to express the work done to get the final formula. So how to start? Once again, I am going to start. What is potential is V. Potential at B, I can write it as VB into what is the charge you are bringing is Q2, and that becomes the expression for work done. So once again, it's a very simple formula. You know, potential is work done by charge. So what about work done is potential into charge. Now ultimately potential at B means it is the potential due to Q1 at B. And what is the charge you are bringing is Q2. So I'm going to write what is potential at B can be written as 1 by 4 pi epsilon naught q1 by, what is the distance? Distance is AB. Distance is AB. So AB, obviously I am going to write it as R1 vector minus R2 vector, but we are concerned with magnitude only. I am writing R1 vector minus R2 vector into Q2. So this is the work done in bringing the charges from infinity to their respective location. I am going to assume let R1 vector minus R2 vector is equal to R12. For simplicity, we are assuming R1 vector minus R2 vector is R12. So therefore, the equation becomes W is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. Yes. Now you know this work done gets stored as potential energy. So I'm going to replace W with U, and it becomes U is 1 by 4 pi epsilon naught Q1 Q2 by R12. Once again, I am going to explain the entire derivation. What is electrostatic potential energy? It is the amount of work done in bringing the charges from infinity to their respective location. Ultimately, that is the definition of electrostatic potential energy for a system of point charges. For simplicity, we considered a system having only 2 point charges. We are going to derive an expression for electrostatic potential energy of a 2-point charge system. So how we started? We considered a coordinate frame in which we assumed 2 charges q1 and q2 with position vectors r1 vector and r2 vector. Initially, in order to calculate the potential energy, let us suppose that the two charges are at infinite separation away from their respective location. Now, you bring Q1 from infinity to its respective location, that is A. I said in this case no work will be done because there were no charges present in the system that will give an opposition due to the electrostatic force. Now, bring Q2 from infinity to B. Surely when Q2 is brought from infinity to B, work has to be done because Q1 already occupied its position. So what about that work done? We are writing it as potential into charge. It's a very simple formula I am using to get the work done. What is that work done is? Potential into charge. So what is potential is? Potential due to Q1 at B into what is the charge you are bringing is Q2. By writing the formula, I am getting W is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12, and this work done gets stored as electrostatic potential energy in the system, that is U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. I am going to extend it for a 3-point charge. So I think you can easily guess. I am going to make a cyclic notation. So how to start for a 3-point charge? It can be written as U is equal to 1 by 4 pi epsilon naught. It will be common. So what is the first set is Q1 Q2 by R12 plus, make the second cycle, Q2 Q3 by R23 plus Q1 Q3 by R13. I think all the sets is repeated. So this will be the formula for electrostatic potential energy of a 3-point charge system. Similarly, you can write this in summation format. How to write in summation format? U will be 1 by 2. I am going to say the reason for 1 by 2. 1 by 4 pi epsilon naught. I am going to put two summations. One summation I equal to 1 to 3. Second summation j is equal to 1 to 3, where j not equal to I. J not equal to I. What about the repeating terms? Q is repeating Qi. The second is also repeating Qj by Rij. Obviously, this is the summative form of a 3-point charge system. So once again I am going to say this logic will be very clear. But what is the purpose of putting 1 by 2? You know, while putting the summation, every set of two charges will be written 2 times. But in the formula it is only 1 time. For that we are multiplying it with 1 by 2. So 1 by 2 is just to avoid the repetition of the sets of charges. That's all. So extending for n charges, how to write for n charges? I think now you can have a very clear guess. U is equal to 1 by 2. I am going to start 1 by 4 pi epsilon naught. Two summations. Say it is j is 1 to n, I is 1 to n, and you know j not equal I. Once again it is Q I Q j by R I j. I think the mathematical form for n charges is very clear with this formula. So once again this expression shows the electrostatic potential energy of n-point charges. Once again, what about 2-point charges is? It is 1 by 4 pi epsilon naught Q1 Q2 by R12. If it is 3-point charge, you make a cyclic rotation of all the sets, Q1 Q2 by R12, Q2 Q3 by R23, Q1 Q3 by R13. So similarly you can write the summation form. Summation form is only for representation, but mathematically if it is for charges, you are going to use this formula. Sometimes this potential energy is also given a term, the expression for association of charges. It is sometimes also referred as expression for association of charges. So in a question they are asking what is the energy required to associate a system of charge. So ultimately this is the expression you are going to derive. So while doing some numerical, they may be asking what will be the energy required to dissociate the system of charges. So in that case I am going to put minus U. That's all. I am going to put minus U. This means U is the energy required to associate the charges of the system, whereas minus U will be the energy required to dissociate the charges of the system. So this is our second topic, that is electrostatic potential energy due to a system of point charges. Yes. Our next topic is equipotential surface. I think by the name itself you can say What do you mean by equipotential? Equipotential means if I am going to assume a surface which has same potential at each and every point. Once again, if I am going to assume a surface with same potential at each and every point, that surface can be termed as a equipotential surface. Now, equipotential surface can be drawn for any region if there is an electric field. If there is an electric field, we can draw the equipotential surface. So, before getting into the pattern of equipotential surface, let us discuss the important properties of equipotential surfaces. So, one by one I am going to explain. Every property is very important because such properties comes in short questions. So, I am going to get into the very first property. If I am going to assume this is an equipotential surface, I am going to assume 2 points, say A, another point is B. If a test charge Q0 is moved from A to B, no work will be done. So what is the first property? The work done is 0 in moving a test charge over an equipotential surface. We are going to prove this. Once again, no work is done in moving a test charge over an equipotential surface. So how to prove this? You know how to write the potential difference? Yeah, work done. You know it is VB minus VA is work done, that is AB on the test charge Q0. Now since it's an equipotential surface, VA should be equal to VB. Once again, since the surface is an equipotential surface, VA is equal to VB. So ultimately VB minus VA is 0. So 0 is WAB by Q0. So this leads to WAB is equal to 0. Once again, this is the first property of equipotential surface. So what it says, no work is done in moving a test charge over an equipotential surface, that is the work done is 0. I am going to get into the second property, the most important property. The electric field is always at right angles to the equipotential surface. Once again, what I am saying is the electric field is always at right angles to the equipotential surface. So how to prove this? I am going to assume the same diagram. So already we proved the work done in moving the test charge from A to B is 0. We proved this. Now we are going to say how the electric field is with respect to the equipotential surface. It is always at right angles to the equipotential surface. So how to prove this? You know, since the work done is 0, the force should be perpendicular to the displacement. Once again, since the work done is 0, if work done is 0, the force should be perpendicular to the displacement, then only the work done can be termed as 0. Now, what about the displacement? The displacement is along the equipotential surface. The displacement is along the equipotential surface. Therefore, the force should be perpendicular to the displacement. The force should be perpendicular to the displacement, and if force is perpendicular to the displacement, this leads to the electric field, that is QE vector. This means E should be perpendicular to the displacement. Yeah, ultimately I can say the electric field is always at right angles to the equipotential surface. Once again, it's a 2-mark question that is usually asked in board. Why the electric field is always at right angles to the equipotential surface? So what is the reason I am going to say? Since the work done is 0 in moving a test charge from one point to other over an equipotential surface, the force should be perpendicular to the displacement. Since the displacement is along the equipotential surface, the force and hence the electric field should be perpendicular to the equipotential surface. So this is our second important property of equipotential surface. Now get into the third important property. Equipotential surface helps us to distinguish the region of strong and weak electric fields. Once again, equipotential surface helps us to distinguish the region of stronger and weaker electric field. So how to establish this? I am going to assume the formula that we derived. Electric field is the gradient of potential. You know, E is equal to minus dV by dr. You know dV is constant for equipotential surface. Let us assume dV is constant for the equipotential surface. This means dr is proportional to 1 by E. E is proportional to 1 by dr. This means the electric field and the distance are reciprocally related. So what this says, where the equipotential surfaces are closer, the electric field is stronger, and where they are far apart, the electric field is weaker. So once again, the closeness, the relative closeness of equipotential surface represents the stronger electric field, whereas if they are far apart, it represents a weaker electric field. That is clearly established by this expression dr is proportional to 1 by E. On about the fourth important property, no two equipotential surface intersect each other. Just like we studied, no two lines of force intersect each other. Similarly, we are going to say two equipotential surfaces never intersect each other. The reason you know, wherever they intersect, the electric potential will be in two direction. That is not possible. So once again, what is the fourth property? Two equipotential surfaces cannot intersect. The reason is, if they intersect, the electric potential will have two direction. You have two values, which is not at all possible. Now, I am going to get into the concept of pattern of equipotential surfaces. So you can see the board. Now I am going to discuss the different shapes of equipotential surface. Obviously, this is also the most important part of equipotential surface, because this section is very important for our board questions also. So for different symmetry, they may be asking for the pattern of equipotential surface. So let us start from, we are going to draw equipotential surface for a uniform electric field. So our first aim is to draw equipotential surface for a uniform electric field. So first of all, we can establish a mathematical relation. Already we know electric field is the gradient of potential, that is dV by dr. Now since dV is constant, I am going to neglect this negative sign. Let us suppose that I am concerned with magnitude terms only. So what this says, since the electric field is uniform, what I can write is dV is directly proportional to dr. What is the conclusion I am going to get is dV is directly proportional to dr. Since it's a uniform electric field, what is the conclusion I am getting is dV is proportional to dr. So what do you mean by this? We are going to draw normal to the direction. For example, they are asking draw equipotential surface for uniform electric field acting along x-axis. Let us suppose that you are going to draw equipotential surface for x-axis. So let us suppose that this is the direction of x-axis. So what you are going to draw? You are going to draw planes normal to x-axis. You are going to draw planes normal to x-axis, and obviously that will be parallel to yz. If they are asking for x-axis, it will be normal to x-axis, whereas it should be plane parallel to yz. So obviously you can see we are able to see three planes. We plotted three equipotential surfaces, 1, 2 and 3 for this uniform electric field acting along x-axis. All these planes are at equidistant. The most important property is, if the field is uniform, what about the planes you are going to draw? They should be at equal distances. So what is the potential of the first plate is V1, V2 and V3. The distance of separation is D1 and D2. So what should be the two distances? D1 should be equal to D2. And this is the case for uniform electric field. Number 2, say if in a question they are asking, you can see the second figure, obviously there is a difference between the first and the second. If they are asking, you are going to draw equipotential surface for a uniform electric field that increases along the, say, x-axis. The value increases uniformly along the x-axis. So once again, say this is also x-axis, I am going to mark, say this is x-axis. So the only difference is, here also you are going to draw planes normal to the electric field, but the difference is, as we go along the increasing direction of electric field, the separation between the planes will decrease. The separation between the equipotential surfaces will decrease. So you are able to see D1 is the separation between V1 and V2, D2 is the separation between V2 and V3. So obviously you can say D1 is greater than D2. So the only difference between the two figure is the separation of the planes. So this type of questions are usually asked in the boards. Second, what about the representation of equipotential surface for an isolated positive charge? I think these are the very simple representations. Already we know this arrow shows the electric lines of force. So I am going to draw concentric spheres about the charge. Those concentric spheres can be termed as equipotential surface. Now a question comes, whether those spheres will be at equidistance, just like what we draw in a uniform electric field. The answer is no, because already we established dr is proportional to 1 by E. So obviously there is a difference in separation of the equipotential surfaces around a point charge. So you are able to see three equipotential surfaces, 1, 2 and 3. Initially you can see 1 and 2 are closer. This means the electric field is stronger, and as we move apart, there is a separation, increase in separation, that clearly says that the electric field is weaker. That is one property we studied, where the equipotential surfaces are closer, the electric field is stronger, and where they are far apart, the electric field is weaker. with the concept of equipotential surface and the properties we studied, I think you can try to draw different shapes of equipotential surface for different configuration. I did some of them. So you can practice for a dipole, you can practice for a set of equal charges and so on. I'm going to get into the last topic of electric potential, that is we are going to derive an expression for electrostatic potential energy of a dipole. Our aim is to find what is the electrostatic potential energy of a dipole. To get the expression, I am going to start from a familiar expression. We know what is the torque experienced by a dipole. Tau is Pe sin theta. I am going to mark it as equation number 1. Once again, if a dipole is placed in a uniform electric field, already we derived it experiences a torque, and torque is tau is equal to Pe sin theta. Now, I am going to assume what is the small work done in rotating the dipole through a small angle d theta against the torque can be written as dw is equal to tau d theta. Once again, work done can be obtained only whenever we are going to do something opposing. So in that case, what I am going to do, I am going to rotate the dipole through a very small angle d theta against the torque. In that case, what is the small work done dw can be written as dw is equal to tau d theta. Mark it as equation number 2. I think you can put 1 in 2. What happens? Put 1 in 2. So dw is equal to Pe sin theta d theta. So obviously this is the small work done in rotating the dipole through a very small angle d theta. Let us suppose that the dipole has to be rotated from an initial angle theta 1 to a final angle theta 2. I think you can clearly guess. In that case, by integration, the total work done becomes W with the limit theta 1 to theta 2 Pe sin theta d theta. You know Pe comes out of the integration. Sin theta can be written as minus cos theta with the limit theta 1 to theta 2. By putting the limit and interchanging, I am writing directly Pe cos theta 1 minus cos theta 2, and you know this work then gets stored as potential energy. So I am replacing W with U. So this is the final form of electrostatic potential energy stored in a dipole. Now we are going to have a sub case. What is the case? Initially, I am going to assume the dipole was perpendicular, that is 90 degree. Later, it is turned through an angle theta. So obviously, initially the orientation was perpendicular. After that, theta 2 becomes theta. Put it back. So I am getting U is equal to Pe cos theta 1 is 90 minus cos theta. So ultimately cos 90 is 0. So it becomes minus Pe cos theta. So this is the magnitude form. If in vectors, if I am going to write, U is equal to minus P vector dot E vector. You know cos theta is the output of dot product. So minus Pe cos theta can be written as minus P dot E. So this is the expression for electrostatic potential energy of a dipole. Quickly I am going to explain. What is the torque acting on a dipole is Pe sin theta. Mark it as equation number 1. Small work done in rotating the dipole through an angle d theta against the torque is dw is tau d theta. Put 1 in 2. Next, I want to rotate the dipole from an angle theta 1 to theta 2. So what about the total work done comes to be Pe cos theta 1 minus cos theta 2. This work then gets stored as electrostatic potential energy. What is the sub case we assumed is initially the dipole is perpendicular, then it is turned through an angle theta. In that case, we are going to show that is U is equal to minus P vector dot E vector. With this, I am going to end my session. Take care of yourself. Thank you.